Hi everyone, my name is Leon Starr, and my recorded face in a box is just here to welcome you to this pandemic edition of my 2020 xtUML Days talk. A live version of this face, in a possibly less creepy box, will take your questions in about 20 minutes. These days I head up the model-based systems engineering effort at the Toyota Research Institute in the Autonomous Driving Division. Also, through my own company Model Integration, I continue to teach classes in requirements analysis and executable UML, as well as develop advanced open source modeling tools. And now I would like to share some of the modeling work my team at TRI is developing to improve the safety of fully and semi-autonomous vehicles.
In applying executable UML, we typically carve out a path leading from requirements in some form through a vicious cycle of analysis and modeling. We compile our models, do a lot of testing and validation, and, if all goes well, we end up with our production code running on our target platform. When I arrived at TRI, I found myself in a research rather than a product environment. We do have an existing software-hardware platform and a whole fleet of vehicles driving themselves around. This platform is constantly being updated with impressive new capabilities by our developers and researchers. I realized that interposing an unfamiliar model-driven development process in the midst of all this activity would create a lot of friction and confusion, and as modelers, that's the last thing we need. So I decided to take a different approach with our workflow. Rather than playing catch-up with existing software features, we decided to leap ahead of the current capabilities and model the actual world in which the vehicle must drive and the end goal behaviors. We don't worry about the specific algorithms to control vehicle motion used to locate the vehicle, detect traffic and pedestrians, and so forth. Our researchers in machine learning can figure all that out. We assume that the world can or will ultimately be accurately perceived by our technology. We assume that we know where the vehicle is and we can control it safely. The question is, given an arbitrary driving platform, does it behave correctly in a given environment? Is there some set of semantics that we can identify that can be assembled to define arbitrarily complex road and traffic scenarios? If so, we can use our modeling approach to generate evaluation code that can be run against real or simulated vehicles. We all know, for example, how to perform a safe lane change, whether we are driving or telling a young driver how to perform the maneuver. This information can be captured in an executable model. That model, in turn, can serve as a gold standard whose behavior can be correlated against any given platform or platform version. Later in this presentation, I will show you an example of how we can generate a lane change evaluator that can be run against a variety of driving platforms or platform versions. By taking this approach, we have been able to provide early results not just helpful to testing and validation, but useful for functional safety by exposing corner cases as well as for requirements definition and systems engineering in general. Before diving in, just a few words about the Toyota Research Institute where I work. Here's one of our latest driving platforms, which we are developing in two modes. Chauffeur mode on the right is the classic 100% self-driving car. Our goal is to make it uncrashable. This is admittedly a lofty goal, not just for us, but the industry in general, despite what the tech media and certain Twitter personalities might have you believe. This is why we are putting substantial effort into Guardian mode. Here the goal is to augment human reaction times and capabilities. So imagine, for example, you are driving along and a car suddenly pulls out behind a truck parked in front of you. Also imagine that you're aging. I was going to say grandparents, but let's face it, none of us are as fast as we used to be. You're not quite quick enough as you grab the wheel, so Guardian will amplify the response and safely guide you around the obstacle, seamlessly returning primary control back to you. This really encapsulates the spirit of Toyota in both our driving and robotics divisions. Our goal is not to replace humans, but to augment human capabilities so that we can do what we love to do safely, even as we age. Now let's come back and look at the driving problem. From a software perspective, it looks daunting. There's so much going on in this scene. How is an uncrashable, self-driving car going to make sense of all of this? Where is it okay to drive? Where isn't it? How do you respect all of the rules and not hit any pedestrians? Worse yet, this is just one example scene in a world of infinite variety. And also, this is an intersection in the USA. It certainly doesn't look like one anywhere in the UK, or Sweden, or Japan. And even in the USA, there are lots of regional variations. The driving environment in San Francisco, California, for example, is a bit different than that of, say, Santa Fe, New Mexico. And we haven't even factored in snow and rain and time of day. Now look at it from a human perspective. Your inexperienced 17-year-old son or daughter can probably get through here with little difficulty. You can quickly reason where you can drive, where you can't, where and when you should stop, where you should yield, and so forth. Why is it so easy for us and so difficult from a computing perspective? I believe that part of the answer has to do with how our brains automatically filter information, and there are some parallels with our concept of subject matter domains. On any executable UML project, we know that the first thing we need to identify is the application domain, which encapsulates the business purpose of our system. So what is the business purpose of our system? Well, if we are building an uncrashable car, it's not to crash. Plain and simple. Go the places you need to go, and don't hit or endanger anything along the way. We call this the vehicle guidance domain, not to be confused with low-level vehicle control. So the mission of this domain is: don't hit any pedestrians or vehicles, change lanes safely, respect traffic signals, basically follow the rules, and drive defensively. Let's take a concrete example. Pun absolutely intended. Imagine directing the vehicle to get in the left lane, hang a left at the upcoming intersection, and end up in the leftmost lane on the other side. The elements that influence this progression of steps are at a minimum: the road, lanes, lane crossing policy, allowed turn movement, intersection, crosswalks, and oncoming traffic. But let's hold on for a moment. We can easily find an endless set of features and low-level behaviors necessary to get all this to work, and succumb to so much complexity that we'd be tempted to abandon modeling altogether, and just hope that machine learning could solve all our problems somehow. This is where I take a deep breath and tell you what 40 years of modeling have taught me as the most fundamental tool for wrangling seemingly infinite complexity. Are you ready? On the next slide, I'm going to give you the modeler's answer to the ultimate question of life, the universe, and everything. Seriously. Are you ready for it? Here we go. The true power of a model comes from what it excludes. You're welcome. I imagine that's only slightly more satisfying than 42, but let me elaborate. In our vehicle guidance domain, we need to include road structures such as lanes, lane boundaries, and so forth, but we'll exclude paint, reflectors, bumpy dots, and any other road marking technology. To accomplish this domain's mission, we just need to know where the lane divisions are and what policies they reflect. The marking artifacts change over time and vary wildly by region. More to the point, weather and construction can redefine the lane divisions at any moment. Even more to the point, symbolic interpretation is its own distinct subject matter that is not specific to roads. We model traffic signals and instructions like stop and go, but we exclude the signaling technology. Again, this technology also varies over time and is highly region-specific. Furthermore, we need to focus on the signal semantics and not the signaling mechanism. A stop signal could come from a traffic officer's hand gesture, for example. We model surrounding vehicle and pedestrian traffic, but we exclude the algorithms for categorizing, monitoring, and detecting the traffic. Distinct subject matters such as perception, pattern recognition, and path planning are better employed to solve these problems. And we just keep on excluding things like vehicle control, devices and sensors, certainly anything specific to a particular driving platform. All this exclusion buys us two things. First, our application subject matter is greatly simplified. We can focus on what matters and get the problem solved correctly. Second, and this is huge, stability. The semantics necessary to describe roads and driving policies haven't changed much in the last 40 years. How you get through an intersection, how you make a lane change, how you enter a driveway. All the supporting structures, policies, and behaviors are pretty stable. Now, they do vary somewhat from region to region, but those differences can be parameterized. For example, we can refer to inside and outside instead of left and right, so that the same lane change model works both in the United States and Japan or the UK. Now let's come back to that intersection I showed at the beginning and see how we can use a model to interpret the scene. The diagram thumbnail on the left is a class model for one of the many subsystems inside the vehicle guidance domain. This subsystem focuses on basic road structure. I realize it is too small to read. That's intentional, so stop squinting. Now we're going to use this model to parse the road structure we see on the right. The goal is to account for all of the critical features in the scene. We start out by identifying the two intersecting roads and then populating the road class. By definition, every road has a right and a left edge, and that is true anywhere in the world, by the way, so we populate all the edges. Now for ease of presentation, we'll limit our attention to the road segment in the foreground. We identify its forward and reverse conduits. A conduit is defined as a set of adjacent lanes all flowing traffic in the same direction. We mark off all of the lane divisions, noting those that are soft or hard. We may not care about paint, but we do care about physically non-traversable boundaries. We pick off the restricted and unrestricted driving lanes. Note that we use specification classes to parameterize restriction policies so that we need not subclass every flavor of restriction lane. Finally, we mark off a couple of exclusion lanes, which are lanes where you are not allowed to drive. One of these includes an island. And keep in mind that in actual use, this model would be continually populating itself, creating and deleting instances as the vehicle drives along. And of course, there are about 75 pages of documentation recording all of our modeling decisions and backing them up with street view examples and references to relevant transportation and road engineering standards. The model of the road environment establishes real-world constraints on our vehicle's behavior. You can't make a right turn if there's no adjoining road segment or driveway. But how do we specify a specific safe maneuver, say a lane change? The trick is to formalize the relevant relationships between our vehicle and the elements of the environment that it needs to interact with. Take a driving lane, for example, as opposed to a non-driving lane such as a shoulder or a bike lane. If an ego vehicle, that's what our industry calls the vehicle we are driving, is on a road, it is an on-road vehicle, as opposed to one that is in a parking garage. Now, if that vehicle is in a driving lane, it is an ego vehicle in a driving lane. Notice how we are specializing without resorting to generalization relationships. Now, when this ego vehicle wants to change lanes, it must select an adjacent target lane, which of course has to be a driving lane. The attributes are omitted here, but I can assure you we constrain the model to ensure that only a driving lane in the same conduit may be selected. Our relationship to a target lane is, in fact, our lane change. It has a born and die life cycle that we'll look at on the next slide. Before moving on, we do need a place to keep parameters that influence the lane change as well as other behaviors. So we model a driving profile that establishes a personality for our vehicle. Part of that is our lane change personality, where we can set values for how long we leave the turn signals on before beginning our maneuver, or how long we wait after completing a lane change before initiating another one. Okay, let's go take a look at that lane change state model. A lane change begins its life cycle with the intention to move into an adjacent lane on the left or right. First, you have to wait for available space in the target lane. We'll rely on a service domain to do the necessary monitoring for our lane to open up. Once it is available, we put on our turn signal in the appropriate direction. After an adequate time period, remember that was in our personality, we begin crossing into the target lane. Once in the lane, after some delay, we cancel the turn signal and then inhibit any future lane change for another time period. Finally, we declare success and the lane change instance is deleted. Of course, this is what happens when all goes well, and we know that this is often not the case. What if the target lane is never open? What if some jerk gets into the target lane midway through your maneuver? What if you accidentally cross over the line before signaling for an adequate interval? More importantly, how do we know we have thought of every possibility? Well, you all probably know executable UML has an app for that. It's called the state table. The state table crosses all the states on the left with all of the events along the top. Each cell represents a transition in green, an ignore in blue, and a can't happen in red. By the way, I figured out a long time ago how to organize the table so that the states that have to be can't happens form a systematic pattern so that I can focus on the interesting stuff in the upper left. For our example, let's focus on what happens when we are in the indicating intent state for the required amount of time, but end up crossing over the lane division too soon. When this happens, we specify a transition to a newly identified state, which we'll call flag unsafe lane change. We end up discovering the need for a number of such error recovery states. Here we've added states highlighted in pink to show all paths that deviate from the proper lane change. And you can see that flag unsafe lane change state on the left. If we cross over the lane division before signaling adequately, we flag the lane change and proceed into the crossing state without interrupting the flow. Ultimately, though, this is just a visualization, and we rely on the state table for the purposes of code generation and for test coverage. Now that we have a complete model, let's see what it takes to produce the lane change evaluator. As we discuss in our book Models to Code, we eschew monolithic tools in favor of lean open source components that we can string together in various combinations. For example, we express our models using a simple text editor to create a file that does not contain any graphical layout information. In fact, we completely separate the model, classes, states, relationships, etc. from the layout. Our layout style sheets use a lean but expressive language to yield beautiful and precisely laid out diagrams. So we don't need to waste our time pixel pushing when we create or edit diagrams. Plus, we can easily perform configuration management on the models and layouts. We then use a language called Mika, a successor to the Pika language described in our book. The Mika processor outputs C source code, which includes a model-level test harness. It also outputs a beautiful PDF that organizes all of our model diagrams, documentation, and the surrounding Mika code so that we always have both the models and the design in one place. Test cases are expressed using a domain-specific language, which produces code that mates with the test harness so that the test cases can interact with the model-generated code. We drive these test cases using simulated or actual driving data from our logs. Our team wrote some proprietary code to extract events and other information relevant to our tests. The tests output sequence diagrams and test coverage reports. I'm going to finish up by showing you our lane change evaluator in action. On the right, you see an excerpt from an actual drive in the form of a video with lots of time-stamped parameters. I'll play that in just a moment. On the left, we have a generated sequence diagram for that lane change state machine I showed you earlier. As the vehicle on the right proceeds through a lane change, we scoop up the associated events and feed them into our state machine. If all goes well, we should drop through the progression of states for an ideal lane change. But if any of those pink states that we saw are entered, we can flag the problem. Now, when I run the test case, we see that the lane crossed event occurs while we are in the intent indication state. In other words, we observe the vehicle crossing into the target lane before signaling adequately. Okay, it's summary time. Model-generated code can be used both to define a system and to evaluate an existing system. So if you're working on a safety-critical project with an existing platform, one approach you can take is to model the application domain. Then use those models to validate the system. A good set of models will uncover all kinds of nasty edge cases. Furthermore, they will expose just how sparse the existing test coverage is and just how incomplete the existing requirements are. Evaluation models provide early benefits for functional safety, test coverage, and requirements definition. The results you get help you make the case for further modeling, both for evaluation and possibly for system development. A flexible and evolving pipeline of open source tools make it easier to demonstrate results and produce attention-getting deliverables. By leveraging existing open source tools and modifying them to suit your needs, you can do amazing things. The tools should amplify your capabilities, not restrict them. Don't ever let your tools define what you can and cannot do. And when it comes to modeling, get good at excluding the right details. This will allow you to build powerful models quickly that make meaningful contributions to your project.